Hydrogen as an alternative energy carrier is considered as the future as more technology is trying to implement hydrogen as the energy sources. In this video, we will be explaining the hydrogen production process using steam methane reforming process. The process is coupled with a CO2 removal unit and a H2 enrichment unit to ensure that the product from the process is up to the standards. The main objective of this project is to produce hydrogen with 99.9% purity at a rate of 30,000 tonnes per year. For CEB2043, Reaction Engineering 1 will be focused mainly on the SMR reactor process, while for CEB2053, Process Modeling and Simulation will be focused on simulating the overall process in simulated software and performing case study analysis on the reactor section. And finally, for CEB2063, Separation Process 2 will be focused on the H2 enrichment unit where absorption technology will be implemented to be further purified.
Next, for CEB2043, Reaction Engineering 1, here are the objectives that will be discussed: types and sizing of reactor, catalyst selection, types of reaction and the reaction kinetics, and finally the strategy to maximize the selectivity and yield of hydrogen. For the first one, PBR will be chosen as the SMR reactor because this reaction is a gas phase catalytic reaction. PBR is chosen because it yields more conversion, has low operating and maintenance costs, and requires low amount of catalyst. For the sizing of reactor, we will be using 850 degrees Celsius temperature and 100 kilopascal pressure. The volume of the PBR will be 200 meter cube with length and diameter of 20 meter and 3.568 meter respectively. Single tube will be implemented in the PBR. For the catalyst selection, we will be using solid catalyst of nickel and alumina with specific surface area of 209 meters square per gram, porosity of 0.65 centimeters square per gram, bulk density of 0.782 gram per centimeter, and composition of 40% nickel and 60% alumina with particle size ranging from 60 to 100 nanometer. Here are the reaction that is occurring in the SMR reactor, which are steam methane reforming and water gas shifting. Here are the overall reaction that will be considered, which are reaction between methane and steam producing carbon dioxide and hydrogen. Here are the reaction kinetics for the overall reaction. It is worth noting that the overall reaction is endothermic with 165 kilojoule per mole enthalpy change. Next, I will be explaining the strategy to maximize the selectivity and yield of hydrogen, which are manipulation on feed concentration, manipulation on temperature, and finally manipulation on pressure. For the manipulation of feed concentration, increasing the concentration of methane and steam can increase the yield of hydrogen based on the stoichiometric coefficient. Next, manipulation on temperature. Based on the Le Chatelier principle, increasing the temperature will favor the endothermic reaction, where SMR process is an endothermic reaction. Next, manipulation of pressure. Based on Le Chatelier principle, decreasing the temperature will shift the reaction towards site with greater number of gas moles based on the overall stoichiometry. By lowering the pressure system, will increase the yield of hydrogen. Here are the stoichiometry table for the overall reaction, including species of methane, steam, carbon dioxide, and hydrogen. Here are the general calculation which include delta and epsilon, the gas expansion factor. Here are the conversion for the reaction, which we calculated to be 0.7552. Here are the initial flow rate for each species and the total initial flow rate before entering the PBR. And here are the outlet flow rate out of the PBR for each species and the total outlet flow rate. Here are the concentration for all species in the outlet of the PBR. And finally, here are the calculation for the weight of catalyst, which we implement the 5-step algorithm, which are the first step is mole balance, second step is rate law, third step is stoichiometry, and the fourth step is the combining all the information, where we calculated that the catalyst needed will be 121.84 kg of catalyst.
Next, we will be going through CEB2053 or Process Modeling and Simulation. For this part of the integrated project, there are three main objectives, which is to simulate the process of hydrogen gas production via the reactor. Next is the comparison between manual calculation and simulation calculation. And then finally, sensitivity analysis. So the main reaction that takes place in the PBR reactor is focused on this overall reaction over here. Now in symmetry, the simulation that we are using, PBR is not supplied, so it is used in theory, but in the simulation, we are using PFR. And the main product stream will undergo two separation processes, which are carbon dioxide removal and hydrogen enrichment. We simulate the process by first selecting a fluid package, which is advanced Tang-Robinson, and then include the components included, use the values from CEB2043 and everything, and then finally, we have this process flow diagram of the reactor only. From these values, we can also integrate the separation processes, which is PSA, and the absorption process, and we will have the whole process flow diagram in symmetry. Next is the calculation comparison. Now, the main calculation focused here is the mole flow rate, the outlet side of the PFR, because this indicates the performance of the reactor the best. Now in the simulation, it gives 957.03 kmol per hour. However, the manual calculation shows 921.2227 kmols per hour. Utilizing the deviation error equation will give a 3.89 deviation error. This deviation error is not optimal, however, it is not too high. The deviation error may be due to human error or some difference in initial values by a small margin or percentage when compared to the simulation calculation. And finally, the sensitivity analysis of the reactor performance. There are four variables: the effect of pressure on the reactor performance, temperature, feed flow rate, and lastly, composition. For the first variable, the effect of pressure on reactor performance. As you can see from the graph and data, pressure increase, mole fraction of hydrogen increase, the reactor performance increases as well. Looking at it backwards, this is because there is an increase in pressure drop, which increases the volumetric flow rate in the streams as well. This will decrease the resident time of the stream, and it will decrease the conversion factor, thus a lower hydrogen product is produced, and vice versa. Next, the effect of temperature on reactor performance. Now from the data, we can also conclude that the increase in temperature increases the mole fraction of hydrogen. We can look at the reasons in two theories. First is the kinetic theory, where an increase in temperature, the molecules and vibration movement will increase as well. The flow rate will increase, and then the hydrogen product produced increases as well. Other than that, we can also focus on the conversion factor. An increase in temperature will cause the conversion factor to increase. The number of molecules converted to hydrogen will increase as well. And then we have the feed flow rate on reactor performance. How does it affect it? It is visualized in ratio to simplify the plotting of the data. An increase in mass flow rate will increase the hydrogen mole fraction. A slight decrease is observed because of other parameters that become limiting factors. Thus, the mass flow rate hits an upper limit and causes unreacted reactants and a decrease in hydrogen produced. Lastly, for composition, it is also the same, visualized in ratio, and a slight decrease is observed because of limiting parameters, and it hits an upper limit and less hydrogen is produced.
Next, we will proceed to separation process to subject. So for this subject, I will cover on type of adsorbent use, isotherm, design of adsorption column, design of separation unit, and also strategy to achieve 99.9% of hydrogen purity. So for the first one is type of adsorbent we use is activated carbon or AC due to its large surface area which can provide larger adsorption capacity than the other adsorbents. AC is also cost saving due to its large micropore and mesopore volumes, which means there is a large internal surface area in a limited volume. For the isotherm we use is Loong isotherm based on the equilibrium data of each component on activated carbon. So as we can see here, the graph show a linear graph or a linear line compared to other isotherm. We can conclude here that all this data or all these results were fitted with the Loong equation. To design the adsorption column, we made a few assumptions. So first, we assume that the breakpoint concentration is obtained at C over C naught is equal to 0.01 or y-axis is equal to 0.01. And then the breakthrough curve is symmetrical at C over C naught at Ts, which means also Ts is equal to Tt, where Tt is time equivalent to stoichiometric capacity. And then based on our research, also we found that the total bed length or column height is 1 meter and also the diameter of the column is 2 cm. To calculate the mass transfer zone, from the graph, the approximate values of TB and TS were determined at TB or breakpoint time is equal to 700 seconds and TS, which equal to TT, is 750 seconds. So we can find the MTZ by using these two equations. So for the first equation is HB is equal to TU over TT multiplied by HT, or use bed is equal to the ratio of TU over TT multiplied by the total length of the column. And then we can get the HB or use bed length is equal to 0.93 meter. For the second equation is we use the total bed length is equal to the summation of used bed length and also unused bed length. So to find the unused bed length, we can minus the total bed length of 1 meter with the used bed length, which is we have obtained earlier 0.93 meter. So the unused bed length is 0.06 meter. So this means the MTZ or mass transfer zone is equal to 0.067 meter. So in summary, the final design of our adsorption column with the total height of 1 meter and also diameter of 2 cm, we found that the mass transfer zone is 0.067 meter. For the separation unit design, the type of unit used is pressure swing adsorption or PSA, as its adsorption separation process operates at a short cycle time while achieving a higher productivity. The material used to construct this column is carbon steel and also nickel aluminide or Ni2Al3. This carbon steel is coated with Ni2Al3, which has good oxidation resistance at elevated temperature and also good corrosion resistance to counter the issue. For the configuration, the single column is the simplest configuration that suits the adsorption column with short MTZ that has 3 to 5 times shorter than its bed column length. As our design adsorption column has very short MTZ, which is 0.067 meter, it was determined to use the single configuration. In order to achieve 99.9% purity of hydrogen production, here we propose two ways. For the first way is increase the number of adsorbent beds. When there are more adsorbent beds used, area in contact between the adsorbent and also the solid also increases, causing more solids to be absorbed by the adsorbent, so the purity of hydrogen will increase. The second one is increase the length of unused bed so that more adsorptive components moving towards the end of the column are adsorbed during the concurrent depressurization steps.
Now we are at the last part, which is conclusion. For the reaction engineering 1, PBR or the long name is packed bed reactor was chosen as the reactor for steam methane reforming process. However, PBR will be used for the simulation since it is close to PBR function. The reaction involved in the production of hydrogen as steam methane reforming and water gas shifting. Reactor sizing determined and 3 different strategies expected to help increase the selectivity and the yield of hydrogen as the product. For the process modeling and simulation part, the estimation of the product, conversion, flow rate of stream, and parameter of the reactor achieved by using symmetry software. Small deviation found with possible human error and small difference in initial value for simulation and manual calculation. Sensitivity analysis conducted by using different variables that affect the performance of the reactor, which are pressure, temperature, feed flow rates, and composition. Now move to the conclusion for separation process 2. Pressure swing adsorption, or the simply name is PCA, was selected to use as the separation process pipe. Activated carbon was used as adsorbent for hydrogen purification for the size-able surface area and low operation cost. Strategy to achieve 99.9% purity of hydrogen proposed by increase the number of adsorbent bed and increase the length of unused bed.